Every single time an X-ray is taken, it all starts with one choice. An operator sets a value called milliamperage, or MA. Now, it looks like just a simple number on a screen, but that one command, it unleashes this incredible torrent of energy, a whole chain of events with really high stakes. So let's dive into what that choice really means. It all begins right here at the control console. This is the bridge, really, between the operator and the powerful physics about to happen inside the X-ray tube. Every single button press, every turn of a dial, it's a command, sending very precise instructions to the machine. And one of the most fundamental of all those commands is setting the MA. We know it affects the final image, sure, but what's actually happening when we adjust that number? What force are we really unleashing inside that tube? Well, as we're about to see, this is no small question. The answer involves this really delicate balance that determines, the quality of the image, the radiation dose to the patient, and, get this, whether the very heart of the X-ray machine survives the exposure or literally melts under the strain. All right, so to really get a grip on the power of MA, we've got to look inside the X-ray tube at something called the tube current. This is what MA directly creates. So here's the key. Tube current is simply the flow of electrons. It's this stream of tiny particles traveling from one side of the X-ray tube, which is called the cathode, all the way to the other side, the anode. And the unit we use to measure the size of this stream? You guessed it, the milliamp, or MA. The best way to think about it is like a river. Seriously, a small current is like a slow, gentle little stream. A large current, that's a powerful, rushing river. It's the exact same principle, just with electrons inside an X-ray tube. And this is where it gets really cool, because this shows how everything is connected. When you set the MIA on the console, you are directly controlling a part of the machine called the filament circuit. And this circuit heats up a tiny little wire, the filament, which then decides just how big that electron river is going to be. Let's just walk through that chain reaction real quick. So the operator turns up the MA. That increases the current going to the filament, making it get hotter. This process, it has a cool name, thermionic emission, boils more and more electrons right off the filament surface. And what do more electrons mean? A bigger, more powerful electron river flowing across the tube. It's a direct, totally predictable cause and effect. Okay, so we've established that MA controls the size of our electron river. But so what? What does that actually mean for the X-ray beam itself? This is where we get into the intended consequences of that choice we make at the console. And you know what? The relationship here is super simple and totally proportional. If you use a low MA, you get a smaller electron river, which produces fewer X-rays. That means a lower radiation dose for the patient and less exposure to the image receptor. Now, if you crank up the MA, everything else goes up right along with it. A bigger river, more X-rays, a higher patient dose, and higher receptor exposure. Simple as that. But, and this is absolutely crucial to get, adjusting the MA only changes the quantity of electrons, the sheer number of them. It doesn't affect their energy or their speed one bit. Think of it this way. It makes the river wider, but not faster. The energy, or what we call the quality of the X-ray beam, that's controlled by a completely different setting called KVP. Okay, so far so good, right? You just control the number of X-rays to get the image you need. Simple, but there is a hidden and frankly enormous consequence to this whole process. It turns out it's shockingly inefficient. I mean, just look at this. It's kind of staggering. Of all the massive amounts of electrical energy we pour into that X-ray tube to create the electron river, less than 1% of it actually becomes X-rays. More than 99% of that energy is converted directly into something else. Heat. A tremendous, almost unbelievable amount of heat. And as Dr. Perry Sprouls points out, this isn't just some weird physics trivia. It is the single biggest threat to the machine itself. All of that waste heat can raise the temperature inside the tube so high that it can cause catastrophic failure. And look, this isn't a what-if scenario. This is a real photograph of a rotating anode, that's the target for the electron river, that has been melted and completely destroyed by too much heat. This is the fiery consequence of that simple choice back at the control panel if it isn't managed perfectly. So, okay, you've got this machine that's basically trying to self-destruct with heat every time you use it. How on earth do you solve that problem? Well, it turns out through some pretty brilliant engineering designed specifically to tame all that heat. The key concept we need to understand is heat capacity. The best way to think about it is like a sponge, but for heat. An object with a high heat capacity can just soak up a ton of heat energy before its own temperature gets dangerously high. So the entire goal of modern X-ray tube design is to maximize this property. And engineers have a whole bag of tricks to pull this off. They can change the size of the focal spot where the electrons actually hit. They can adjust the angle of the anode target. They can spin that anode at incredibly high speeds. And they can even change the electrical waveform that powers the whole thing. Let's just take the waveform, for example. A simple single-phase power supply delivers its energy in these pulses, right? This creates intense little hot spots on the anode. But a more advanced three-phase generator gives you a much smoother, more constant stream of energy, and that spreads the heat out much more evenly, avoiding those dangerous temperature spikes. The benefits are pretty obvious when you lay it all out. That three-phase power gives you way more uniform heat distribution. It's more efficient at actually making X-rays in the first place, and because it avoids those nasty hotspots, it gives the tube a much higher effective heat capacity. It can just handle more stress, period. So really, it all boils down to one key principle. Almost all of these strategies work the same way. Whether it's spinning the anode at 10,000 RPM or changing its angle, the goal is to spread that intense electron bombardment over the largest possible surface area, preventing any single point from melting down. So, after all of that, what's the big takeaway here? Well, it all comes down to this fundamental tension that exists at the heart of every single X-ray exposure ever taken. That simple number you dial in, the MA, it's way more than just a technical setting. It represents a constant, delicate balancing act. The operator has to pick a value high enough to create the quantity of X-rays needed for a good diagnostic image, but also low enough to keep that resulting inferno of waste heat within the survival limits of the machine. And that really leaves us with one final big question. Modern imaging, especially in things like CT scans, it demands more power, longer exposures, which all means more heat. So it's a fascinating challenge for the future. How will engineers continue to innovate and win a battle where the enemy is